Welcome to NPTEL online course on fractals and multifractals. So, in the last class we have discussed some properties and computations of fractal dimension for the sets in R power m, that means in the general Euclidean space. Let us continue to compute the fractal dimension of a set in R power m through the iterated function systems. So, here this theorem says that let R power m with n minus 1 contraction mapping forms the hyperbolic iterated function system. That means consider R power m with Wi where I belongs to n of n minus 1. Consider this iterated function system, hyperbolic iterated function system, and this iterated function system has the attractor A. As we know from the iterated function theory, if we have the complete metric space together with the finite set of contraction, we can form the Hutchinson mapping by taking the union of all the map. Then this map is a fixed point of the H of R of m. That fixed point we can denote as the attractor. You can take that attractor as A. Suppose Wi is a similitude of the scaling factor Si for each I belongs to 1 to n minus 1. If the IFS is totally disconnected or just touching, then the attractor has fractal dimension d of A, which is given by the unique solution of sum of I equal to 1 to n minus 1 modulus of Si power d of A equal to 1, where this d of A belongs to 0 comma m. If the IFS is overlapping, then d bar is greater than or equal to d of A, where d is the solution of sum of I equal to 1 to n minus 1 modulus of Si d bar equal to 1, where d bar belongs to 0 comma infinity. Now, here Wi is the similitude of a scaling factor Si. Consider the R power m with the Euclidean metric d. Then what is the similitude of the scaling factor Si? If you are finding the distance between any Wi of x comma Wi of y, which is equal to modulus of Si times distance between x and y for all x comma y in the B belongs to R power m, for all A x comma y belongs to H of R power m. That means any element in the R power m. Now, we will give the sketch of the proof here. Consider the case where the IFS is totally disconnected. This IFS is totally disconnected. Suppose that the scaling factor Si associated with the similitude Wi is non-zero for all I belongs to 1 to n minus 1 and epsilon greater than 0. We begin by making two observations. The observation 1, since Wi is a similitude of the scaling factor Si for all I equal to 1 to n minus 1, it maps the closed ball like this one. So, here we can take the closed ball Bi of x comma epsilon is defined as set of all y such that distance between x and y is less than or equal to epsilon. If we apply the similitude mapping on Wi, then it will transform, the center will transform to Wi of x and the radius will transform to the modulus of Si of W. For proving this one, let take y belongs to here the ball of x comma epsilon. So, From this definition, from this observation, one can observe that distance between x and y is less than epsilon. Suppose if we are finding d of wi of x comma wi of y, we can get modulus of si times d of y x comma y, which is less than or equal to modulus of si comma x epsilon. So, which implies that wi of y belongs to the ball of center wi of x and the radius this one modulus of si times epsilon. So, here this is the definition of the similitude map. Now, for the second part, take z belongs to here ball of wi of x comma si times epsilon, modulus of si times epsilon. Since si is non-zero, we say si is non-zero. So, wi is the invertible mapping. Therefore, the w of d of wi inverse of z comma x, we can write it 1 by modulus of si times d of z comma wi of x. We are applying wi mapping here, therefore, we can get this one, which is less than or equal to epsilon, because this mapping is equal to 1 by modulus of si times epsilon, which is you can cancel this one because this quantity is less than or equal to this quantity, therefore, we can get epsilon. So, wi inverse of z is belongs to ball of x comma epsilon, which implies z can be equal to wi of wi inverse of z. You can apply the wi in both sides, then you can get wi of b of x comma epsilon. So, which implies that we are begin with this set and we ended with here ball of center wi of x comma radius modulus of si comma epsilon is contained in this set wi of b of x comma epsilon. This is one part. From here we can conclude that wi of b ball of x comma epsilon is contained in ball of wi of x comma si times epsilon. Now, we can take us to, because we take the ball from here and it goes to here, from 1 and 2 you can observe that we can observe this result. From 1 and 2 we can observe this result. So, from this observation 1, since wi is a similitude map of the scaling factor si, it mapped the closed ball like this one. That means, if you take the closed ball and find the image under wi, which is equal to find the image of x and make it center, then the radius modulus of si times epsilon, this ball both equal to this ball. That means, the radius is changing, but the ball are same. Therefore, this inequality is true. That means, assume that si is not equal to 0, then wi is invertible and we obtained wi inverse of ball of center x radius epsilon is equal to ball of center wi inverse of x with the radius epsilon over modulus of si. The latter two relationship allow us to establish that for all epsilon greater than 0, n of a comma epsilon equal to n of wi comma a with the radius modulus of Si comma epsilon, which is equivalent to, this is equivalent to n of, if you are applying Wi of A comma epsilon, n of A, this becomes A and this becomes the inverse, that modulus of Si power minus 1 epsilon. So, this applies for all the I belongs to 1 to n minus 1. Now, the second observation, this is the first observation, you can find the minimum cover of A and the minimum cover of Wi of A with the these two radius are equal. Then if you apply the similitude map, then Wi of A here, Wi of A inverse it will become, therefore, by using this relation we can get Wi of A becomes A and this ratio becomes Si inverse times epsilon. Now, second observation, the attractor A of the IFS is the disjoint union because it is totally disconnected. So, A is the disjoint union, that means W1 of A, W2 of A up to Wn minus of A equal to A, where each W of A is the compact set. Hence, we can choose the positive number epsilon so small that if for some positive, some point x belongs to R power n and some integer I belongs to n minus 1, we have all are compact set and disjoint union, we can get A. If we choose one point x belongs to R power n, then ball of the center x and radius epsilon intersects Wi of A comma A with non-empty, that means both will intersect. Then ball of x comma epsilon and Wj of A equal to empty for all j belongs to 1 to n minus 1 with j not equal to I. It follows that if the number of epsilon is sufficiently small, we have, if the number of epsilon is sufficiently small, we have, then the number of boxes required to cover A with radius epsilon equal to, we have the disjoint union, therefore, find the number of box required to cover W1 of A, W2 of A, W3 of A and so on, Wn minus 1 of A with the same epsilon, if you take this sum which is equal to this one. If you put this observation and this observation together, then this equation and this equation in the one, this one becomes, then n of A comma epsilon equal to n of A comma S1 modulus of S1 minus power minus 1 time epsilon, radius you can take the radius and find the number of covers, minimum number of cover of A and S2, S3 and Sn minus power minus 1 time epsilon radius you can find, then this quantity equal to this one. This functional equation is true for all positive number epsilon which are sufficiently small. The proof is completed by showing formally, but this implies the assertion in the theorem. Here we demonstrate the reasonableness of the last step. Let us make the assumption this one. Number of ball required to cover A with the epsilon equal to C time epsilon power minus D in the box counting method to find the D. Then substitute into 2, here we obtain the equation, this one C times epsilon power minus D is approximately equal to, instead of this one you can apply this quantity C S1 power D epsilon power minus D, C plus C times modulus of S2 power D time epsilon power minus D and so on up to this. You can take D, C all common, it will cancel. So, minus epsilon power D also you can take, it will cancel. So, 1 over this sum. So, this summation is summation I equal to 1 to n minus 1, which is modulus of Si power D. So, we can get this which is equal to the desired result which we want to prove. then this D we can call it as the dimension of the set A, because we started by finding the covering of A. So, this can be explicitly stated here. If let this x r power n and this hyperbolic IFS you can consider, these are the contraction mapping on the r power n, it has the attractor A. Suppose each Wi is a similitude with the scaling Si not equal to 0. If the set is totally disconnected or just touching, the fractal dimension of A can be obtained by this equation. It is overlapping, then you can find by here. The first observation, if you are finding the number of cover of A, you need to observe that you can take x as a center, epsilon as the radius, find the ball to cover the A. We need to find. For this one, you have to observe this one. Then from here, we can observe that we have A and the mapping of A and W of A. If you are finding the covering of A, the covering of A with the radius this one, which is equal to finding the minimum number of cover of W of A with the radius epsilon. Then this observation, if the disjoint union, because Wn is the totally disconnected and it is the attractor, that means A can be written as union of these numbers, structure of the attractor. If you observe this one, then the number of A comma epsilon can be written as the union of the sum of the number of covers, minimum number of covers of W of A's, where I is I equal to 1 to n minus 1, which implies that you can apply this property here, then you can get A comma Si power minus 1 time epsilon. Then dividing the dimension, then power law behavior, then you can get this one, then solve this one, one can get this one. For the overlapping set, we can get this one. So, each piece of W is a scaled copy of the whole of A with the scale modulus of Si. At small scale epsilon, the number of epsilon ball needed for A is approximately the sum of needed for all pieces. This self similarity balance gives this equation, because it is written as the union, A is written as the union of this copy. If it is just disjoint and just touching, we can get this one. So, now let us discuss some example related with this theorem. So, this theorem says that if we have the IFS, then obviously we can generate the one attractor for the iterated function system by using the HB mapping and Banach fixed point theorem. By IFS theory, it has the one attractor. This theorem states that how to find the fractal dimension of that attractor. Now, we know that the Sierpinski triangle is generated by these three iterated function system. This contraction mapping we need. By using this contraction mapping, we can generate the iterated function system. Here all the mapping W1, W2, W3 all has the contraction factor 1 by 2. Therefore, there are 3 mapping. So, summation I equal to 1 to 3 mappings, 1, 2, 3, the number of mapping is 3, sum of Si power D of A, which is equal to 1. So, this Si power D of A, so we can get that all the Si is 1 by 2. So, 1 by 2 3 times, 1 by 2 power D of A plus 1 by 2 power D of A plus 1 by 2 power D of A equal to 1. So, 3 times 1 by 2 plus positive number D of A, we can get as 1. If you solve this one, take a ln of 2 side, ln on both side, this ln 1, ln of 3 plus d of a ln 1 by 2, which is equal to d of a, which implies d of a equal to minus ln 3 by ln 1 by 2. This minus d of a, this you can get minus 1 by 3 can get, if you take here then it will goes to here the power, then 1 by 2 inverse becomes to ln 3 by ln 2. So like that we can find the d of a here one can find, then d of a equal to ln 3 by ln 2 is the fractal dimension of Sierpinski triangle generated by the iterated function system, this one. Now the Van Koch curve is generated by these three iterated function system. Now instead of finding the fractal dimension through the set, we are finding the fractal dimension through its iterated function system. Here W1, W2, W3, W4 is the iterated function system consisting this contraction. This 3 contraction mapping as the scaling factor 1 by 3. If you are applying the formula, one can get this one, then same the ln 4, one can get ln 4 plus d of a ln 1 by 3 equal to ln 1, then this will become 0. D of a one can write as ln 4 over minus ln 1 by 3, which is equal to ln 4 by ln 3. So this is the dimension of the fractal dimension of the Koch curve, it is 1.262, and you can observe that the Van Koch curve is embedded in r power 2. Similarly, the Van Koch curve, if you take in k is embedded in r power 2, the fractal dimension of this k equal to 1.262, and similarly this Sierpinski triangle also embedded in the space r power 2, it is then 1.585. So Sierpinski triangle, if you are 1.58 approximately, then if you are finding the, we know that the fractal dimension of r power 2 is, the fractal dimension of r power 2 we obtained is r power 2 is 2. Now you can compare this one. If A is subset of r power 2, then the d of k is less than or equal to d of r power 2, and similarly d of s is less than or equal to d of r power 2. But one can ask the question, in k and s is subset of r power 2, then R4 therefore the fractal dimension of k and s both are less than or equal to d of r power 2, the fractal dimension of r power 2. This is obvious from the theorem, then how can this is different from the classical object with the, how can this k and s is different from the classical object? Since if you are taking the closed interval 0, 1 cross closed interval 0, 1, that means in the filled square, if we find the fractal dimension of filled square, we can get it is as 2, because it is a regular object. We obtained in the last lecture the fractal dimension of this filled square, d of this filled square s dash is equal to 2, which is also embedded in r power 2, which is also embedded in r power 2, but its fractal dimension is 2, which is equal to the embedded space fractal dimension. So here the fractal dimension of Van Koch curve and the Sierpinski triangle both are lesser than the embedded space fractal dimension, one can you need to observe. Therefore this has the fractal nature, and this two object we can call it as a fractal object. So here we are obtaining the fractal dimension of the object, that means the Van Koch curve as well as the Sierpinski triangle, by their iterated function system, not their set. If we are not finding the fractal dimension of Koch curve from the resultant attractor. We are finding the dimension through their iterated function systems. In the last lecture, we have discussed how to find the fractal dimension of given object or given set, whereas here we are obtaining the fractal dimension of the set where it is generated from. So, it is generated from the iterated function system. Through the iterated function system, we obtain the fractal dimension of the resultant attractors. So, thank you. One can refer these two books for more detail. Thank you.